Video, we're going to discuss the strengths of various types of bonds with respect to their Lewis-Dot structure. The distance between two atoms in a particular molecule is referred to as the bond length, and this has to do with the attractive forces between the atoms involved in forming the bond. A covalent radius is the size of an atom in which the atom is attached or bonded to another atom in which there is a purely covalent bond. The radii of the two atoms can be added together, and that should equal the bond length. When talking about Lewis-Dot structures and the number of pairs of electrons that are shared between atoms, we could talk about the so-called bond order. If there's one pair of electrons that is shared, this is referred to as a single bond. If two pairs of electrons are shared, then we refer to this as a double bond, and we can have up to 3 pairs of electrons that are shared, the so-called triple bond. In some cases, you can have situations where there are fractional bond orders. This happens oftentimes when you have resonance structures. At this point, we'd like to consider the effect of the number of pairs of electrons that are shared between two atoms and the strength of the bond that is formed. In the example of forming a single bond, the element fluorine forms a diatomic element where there's one pair of electrons shared between the two fluorine atoms. This is referred to as a single bond, and it turns out that while this is a relatively long bond in comparison to the other diatomic elements such as elemental oxygen, in which there are 2 pairs of electrons that are shared. So this is a double bond. Even though oxygen is a little bit bigger than fluorine, the distance between the two atoms in O2 is actually slightly smaller than that of fluorine. If we go to the element nitrogen, there are 3 pairs of electrons, and in fact the distance between the atoms gets even shorter. So it turns out that generally as the number of pairs of electrons that are shared between two atoms increases, the distance between the two decreases and the so-called bond strength increases. In order to understand the sharing of a pair of electrons between two atoms, we can look at the potential energy diagram shown here, in which we have plotted on the x-axis the distance between the two hydrogen atoms, and on the y-axis we have the potential energy of the overall system. You'll notice that there is a situation where the two atoms are pretty far apart. This then represents the situation where the electrons are not attracting the two nuclei together, but as the distance decreases, we get a stabilization in energy. But then at some point, the two atoms, when they get too close together, then we start to have the nuclei, which are positively charged, starting to repel one another, and the energy goes back up. The optimal distance between the two atoms is because of the fact that the two electrons in H2 spend most of their time between the two positively charged nuclei, therefore attracting the nuclei closer together. In the situation, the most stable distance turns out to be about 74 picometers. This is the average bond length of an HH bond, and represents the most stable distance. If the distance is greater, the potential energy goes up, and at some point the potential energy would reach a situation where the atoms essentially break apart and we no longer have a bond. So this energy difference between the most stable situation and when the two atoms are separated by a very large distance is often referred to as the bond dissociation energy. In order to calculate bond dissociation energy, we have to take into account the amount of energy that we have to put into the molecule to separate the atoms from one another and the number of bonds in the molecule. So, for example, if we take an element such as chlorine, which has a single bond between the two chlorine atoms, and break those two atoms apart and figure out the amount of energy it took to do that, this would represent the bond dissociation energy for chlorine. However, if we have a molecule that has more than one bond in there, then we have a situation where we have to account for all of the bonds. So, for example, methane has 4 carbon-hydrogen single bonds, and so when we put energy into this molecule and break it apart into atoms in the gas phase, that requires 1656 kilojoules of energy per mole of methane molecules. And so to calculate the bond energy for a single carbon-hydrogen bond, we would then go ahead and divide that energy by 4 to come up with a bond energy of 414 kilojoules per mole of for a carbon-hydrogen bond. So it turns out that bond dissociation energies or bond enthalpies can be either positive or negative, but more often than not they are positive because we're putting energy into the system to break the bonds. In order to compare different types of covalent bonds to one another, it's sometimes useful to calculate these bond energies and look for any kind of trends. So the bond distance between two atoms often is correlated with the so-called bond strength. So we would predict that the distance between a carbon and fluorine in a CF bond would be shorter than that of the bond between carbon and chlorine, and therefore we would expect that the CF bond would have a stronger covalent bond, or in this case a polar covalent bond, than the CCl bond. Turns out that this is consistent with the data that is observed, and so shown here are the values for the carbon halogen single bonds, and so indeed the CF bond is the strongest. It is the highest in terms of bond dissociation energy, whereas then we have the carbon chlorine bond, which is slightly weaker, and then the carbon bromine bond, and then finally the carbon iodine bond, which is the weakest. Even though they all have exactly the same bond order, the distance between those two atoms increases as you go down the group for the halogens, and hence the bond strength weakens. Shown here is a compilation of selected data for various bond energies. From the big picture standpoint, you can see that the single bonds generally have bond strengths that are less than that of similar double bonds, and indeed they would be less than corresponding triple bonds. So we can use these bond strengths in a variety of types of calculations and make predictions about overall bonds, energies, and then the heat that might be released when doing various kinds of reactions.